generating functions. So we're going to talk about generating functions, and then we'll talk about random bipart networks, which is a hugely important thing in and of themselves, and you can imagine variations of that. There's some nice generating function stuff for that, but you know, okay. All right. How long will this take? Okay, so yeah, we're going to have just sort of introduce the thing, talk about some basic properties that, and some pieces that are important for these calculations, which may, I don't know if they're used everywhere else and they're common, but they'll be important for what we do here. Yeah, okay, fine. So it's a bit of a dark art, that's true. Very nice. So if you haven't seen generating functions, maybe Fourier transforms, those sorts of things, Laplace transforms, there are lots of melon transforms. You turn something into a melon. There really is. Okay, so it's going to be adjacent to all of that, right? And so it's going to be more, these will be probability generating functions, right? So they're actually, we're thinking about probability distributions, so they have an extra property. But in principle, you just have a string of numbers. You can attach them to some sort of object, right? We're going to multiply them by some blob. And these blobs are going to be interesting kinds of functions that allow us to do some things, play around with these sequences and kind of maybe chop pieces out and merge them and do funny things with them, right? So there's a whole sort of world of playing around. You can do things with decks of cards and stuff like that. So this is going to be a generating function, so a pretty famous object. So we're going to take our sequence and they're going to be starting 0, 1, 2, and so think of these as probabilities. There's a probability that 0 things happen, right? And it's going to be probabilities of integers, right? So when we go to a network and we sample from it, we could have a node with 0 friends or 1 friend or 2 friends, right? That's the sort of game we're playing there. Or we could have an edge that leads to a node that has 0 other friends or 1. So these are the numbers we're interested in, right? But this could be from n equals minus infinity to infinity in general. You could have other kinds of things. So we're going to have this little world here. And yeah, so we're going to have this vector, right? These a's, and we're going to turn it into a function that we can then play around with. We like functions. We can integrate them and differentiate them and multiply them together and stuff like that. So, and again, Fourier transforms, you can think about things like convolutions, which are important, incredibly important things. For filtering, that's a filtering thing. That in Fourier space, that's just a product of the Fourier transforms. So in lots of things where on one side of this sort of strange mirror, things are easy. So you go to you go to this sort of bizarro universe and do the things, and then you come back. Yeah. So if you haven't seen melon, it's really a thing. It's not a melon. It's really a melon. Anyway, so this is going to be a simple one, right? So Fourier, we have cosines and sines and those sorts of things. But we're going to just have polynomials. So x to the 0, x to the 1. And the big piece, the kind of the architecture in here that's going to work for us, if we have an x cubed and x to the 4 and you multiply them together, you get x to the 7, right? So there's 3 plus 4. So we like adding stuff up. We're good at multiplying things together, so we're going to do it all to make a big soup of stuff. Yeah. Okay, so this is throwing a die, rolling dice in general. So, right, the probability that you get we don't have any zeros and we don't have anything above 7, so we're just going to have 1 through 6, and this is going to be our generating function for this object. Right, this is going to be 1/6. This obviously I spent like 5 hours getting that font to work. It's just so worth it. Oh my God. If only we could get emojis into LaTeX, right? Really? We should just leave and just do that now. This is too important. Oh my God. We should have a whole course on LaTeX. It'd be really fun. Let's see, sorry. So it's a 6 for each one, but it's a 6 times x to the 1, 6 times x squared, and that's this blob here. And of course you can factor this out like this, but really sort of think of it as the 6 is hanging around here and here and here. It's stuck to the thing, right? Yeah, okay. Probably if a coin, if we call a head a 0 and a tail 1 arbitrarily, then we could encode, we encode them in that way. So and maybe it could be biased as well, so that's what this is, yeah? Allowing for, but if it's a normal coin, it's a half 1 plus x. So these are nice things. Okay, so what can you do with these little objects? So, so some sort of a fun thing to start with, like just multiply. Why don't we do this? So we've got a half 1 plus x, right? So it's really x, so this is f of x for a coin. I'll just write that. So let's just multiply a couple together, right? So then we'll get a quarter, so a quarter 1 plus x squared, all squared. So it's a quarter 1 plus 2x plus x squared, right? So a quarter plus a half x, and we'll put an x to the 1, x to the 0, plus a quarter x squared. So you can read this off, right? There's a quarter of a chance that you get that your two. So we'll get to this, but basically, if we got 2 coins and we added them up, we're turning their scores, their head or tail, into a score, right? So a head is 0. So we get a head and we record that as a 0, and then we get another head, flip it again, we get another 0, add them together, right? So we've got 0. If we got a head and then a tail, or a tail and a head, our little sum would be 1, and 2 tails would be a 2. And so that's what this is, right? So there's a quarter of a chance of getting 2 tails, and there's a half a chance of getting a head and a tail, either order. And then this is a quarter for 2 heads. So you can imagine more complicated things, right? So what you do is you over in this space, if we're adding, so we're going to add 2 random variables together, and then that amounts to multiplying their generating functions together. So like Fourier kinds of things. Seem okay? And so quite a nice one for Settlers of Catan fans, right? Anyone? We've played this game? Or is it too old now? Let me find a thing to throw away. What is it? No? You still feel like that is it's not a, you youngsters. So this one would be a 6x plus, right, plus x to the 6. Did I get this right? Yeah, so we'd have 1 over 36 squared. So this would be our f of x squared. So it's 1 over 36, and we'd have, x squared plus 2x cubed plus 3x to the 4 plus and you get up to 6. Did I get that right? 6x to the 7, and then it goes down again to 2x to the 11 plus x to the 12. Right, so the probability of getting looks like this, right? So it was a uniform distribution, and now we're going to add these 2 variables, right? We're going to roll 2 dice and add them together, and that gives us this guy, and a 7 in the middle. And so there's a 6 in 36 chance of getting the 7. So 1 in 6, yeah? And I feel like I should put some more in here. This should be maybe 5x to the 8. And then this is a symmetry one here. This is 5x to the 6 plus ... So in Settlers of Catan, I think it's done like this is the number of pips. I got this right? Do they just sort of put this on the card, they do it like that, right? I got that right? I feel like that's wrong. This is the rubber, right? If you roll a 7, you go to the desert land or whatever, or you get to move the rubber and steal people and It's a much better game if you play it cooperatively, actually, where you just try and score a high score as possible. But that's anti-American, so I can't believe I said that. I'll just leave. Just walk straight to Canada. Okay, so yeah, they have those little pips are telling you what they're like, and in fact, it is because it is these linear things. Yeah, very nice, very nice. It always ends very anticlimactically. It's like people are doing all these things, and then I've got 10 points. Okay. Okay. We should totally have a game thing. Yeah. We could start everything with werewolf or something. That would be good. Okay. Okay. So that was just a sample. I'm not saying that this is that, right? It was just sort of like, look, that funny things can happen. Okay. So one thing we'll be really interested in doing is sampling, rolling some funny die, right, with whatever, 37 sides, and it gets some number. And then we walk over to another set of dice, and that we'll take the number from this one, say it's 17, and we'll roll this one 17 times and add all of them up. But this could be a 64-sided die. So this is sort of, it's not adding things together anymore, right? This is a slightly different thing, and that will actually have quite a beautiful form in terms of generating functions, but the operation will be, I want to sample, I roll a thing and it gives me a 3, and that means that I go over to these other shaped die and I'll roll 3 of them and add them up. Yeah. It's a cool problem. And you can see how that's going to work with networks, right? You hit a node and you sample from all the possible number of edges it could have from that R sub k distribution, and you get, say this one has 6 other friends. And then you go to that thing again, and you're going to sample from this edge thing again to get the total number of edges out there, or whatever you want to do, right? Very nice. Or let me say it like this. So you jump on a node, you sample, you find a random node, and it has so many friends, so you sample from the node degree distribution. And then you want to know how many friends of friends that node has, right? So you sample, you get a 7, and then you have to sample from the edge degree distribution 7 times and add all that up. And do that a bazillion times, and you get some new distribution. Right, that's fun. Very nice.